Right. So at the end of the last session, we were talking about the cost and how it's manipulated. And I'm just realizing we didn't discuss how the cost itself is calculated. The cost of a link, let's just say the cost of a link. Right. So OSPF, it uses cost as a metric, and a lower cost indicates a better path. The Cisco cost of an interface is inversely proportional to the bandwidth of the interface. So the higher the bandwidth of the interface, it means the lower the cost. So if we have an interface, a fast interface, a gig interface, a giga Ethernet, and we have a 10 giga Ethernet interface, it means this automatically will have a lower cost because it has a speed of 10 gigabytes per second. Here we have 1 gigabyte per second. Here we have 100 megabytes per second max. Some, they might have 10 megabytes, but let's use 100 megabytes per second. So the cost of fast gig at 10 gig. Here we have the lowest, with fast having the highest. Let's just say. Right. How is it calculated? The formula used to calculate the cost, its cost is equal to the reference bandwidth over the interface bandwidth. And what is the reference bandwidth? The default reference bandwidth that is used by Cisco devices is 100 megabytes per second. So this is the right. So this is the default reference. 100 megabytes per second. This is the same as this one. I think it's easier to take it as 100 megabytes per second. All right. So what does that mean? It means for fast Ethernet, whose interface bandwidth is 100 megabytes per second, what will be its cost? Its cost will be 100 over 100, which is equal to 1. So the cost of a fast Ethernet is 1 by default. By default. Right. Let's calculate the one for Giga Ethernet. For Giga Ethernet, it will be 100 megabytes over 1 gig. And 100 megabytes over 1 gig is 0.1, which will be the cost for a Giga Ethernet interface, 0.1. And lastly, for 10 gig Ethernet, it will be 100 megabytes divided by 10 gig, which is 0.01. So that's how by default the routers, Cisco routers, calculate the cost. So for fast, the cost is 1. For gig, the cost is 0.1. Lastly, for 10 gig, the cost is 0.01 by default. But here we have a problem. The problem is the cost needs to be an integer. An integer means a value 1, 2, 3, 4, 5, not a 0.1. So by default, all these values, they become 1. This one also becomes 1. Fast also becomes 1. And that's a problem. That's a problem because the cost of every interface is equal to 1. By default, the cost of every interface is equal to 1. And that needs to be changed to manipulate the cost, to manipulate the calculation of the cost. That needs to be changed. And how is it changed? It is changed by changing this value here. We change the default from 100 megabytes to, the default is changed from 100 megabytes to, let me see, where is it changed? Okay, the change depends on, you can change using any value you want to use, but logic says the change. So we said cost is equals to the reference over actual. Right, this is the reference bandwidth. Stay with me. Reference bandwidth over actual bandwidth. All right, stay with me. We also found out that fast by default is 1, gig is 0.1, which is 1, 10 gig is 0.01, which is also 1. Right. Logic says it's best for you to change the reference bandwidth. And to which value do you change it? It makes sense to change it to this value here, the highest bandwidth that you have on all the interfaces that you have in your network. So in our case, the highest we have is 10 gig. So what does that mean? So if we change the reference to 10 gig, what will be the cost for fast? In this case, we now have 10 gig over 100 megabytes. So for fast, it will become 10. We've now changed. Is it 10? Let me see, 10, 100. No, for fast, it becomes 100. The cost will become 100. And for gig Ethernet, it will become 10 gig divided by 1. It means for gig Ethernet, the cost will become 10. And for 10 gig itself, is 10 gig divided by 10 gig, the cost will become 1. So here we now have a range of values which are integers to show us the cost of given interfaces, which is correct from the definition that we have. The cost is inversely proportional to the bandwidth. So for 10 gig, it's 1. For 100 megabytes, it's 100. That's how you manipulate, or let me just say change the reference bandwidth so that you can have integer values to show you the cost of any given interface. So in summary, let me see if I can have a table here. In summary, what do I have? Insert a new slide. Okay, title only. Right. In summary, what do we have? We started with cost is equals to reference over actual bandwidth, right? And we had reference default. So default reference, it was equal to 100 megabytes per second, right? From those values, what will it mean? It will mean fast, gig, 10 gig. What will be the values of cost? Right. Right. It will mean cost will be equal to 1 here because we have 100 megabytes, which is the default of 100 megabytes, which is the actual of fast, which is 1. For gig, it will be 100 megabytes over 1 gig. 100 megabytes over 1 gig is equal to 0.1. And lastly, this one over 10 gig is 0.01. And all this cost equal to 1 because we need integer values, which is a problem. We cannot differentiate between fast gig and 10 gig, 10 gigabyte links. So to change that, we change the reference value. So from 100, we give it the highest bandwidth in the network. So the highest is, in this example, we have 10 gig. You see other networks, they also have 40 gig. You can change as well. If you change it to 40 gig, the values of the cost will change as well. But they will be proportional because you are using the same reference bandwidth. So if we change it from 100 megabytes to 10 gigabytes, what will be the cost for, let's start with the 10 gigabytes one. It will be reference over the actual, which is 1. Then for Giga Ethernet, it will be reference over 1 gig, which is the actual, which is 10. Then for 100 megabytes, fast Ethernet, that is 0.1 gig, which is 100 here. So the cost changes. So this is the cost for 100, for reference 100. Then we have another cost for reference 10 gig. So here we've manipulated the value of the reference bandwidth so that we can get integer values for our cost. Basically, this is how you manipulate the auto, the reference using the auto. Okay, here. So this is the value that you just changed. Here you go to auto cost reference bandwidth and you change that value in megabytes per second. So in our example, we had 10 gigabyte link. We use the 10 gigabyte link. So in megabytes per second, what is 10 gigabytes per second in megabytes per second? It is 1,000. I hope it is. Is it 1,000 or 10,000? Okay, it's 10 gigabytes is 123. 123. This is 10 megabytes. So 123. This is 10 gigabytes. In megabytes, it means we have this is megabytes. So in megabytes, we have 10,000 megabytes basically. 10,000 megabytes per second. This is equal to 10 gigabytes per second. So if we want to change our reference bandwidth to 10 gigabytes, we use 10,000 megabytes per second, and you come and change your auto cost reference bandwidth there. That is how you manipulate the cost. That is one way of manipulating it. Another way is to go and directly change the cost value using the IP OSPF cost command. This command here. Let's see how would that be used. Let's delete this. Let's see how would that be used. Okay, move this. Delete that. Okay. All right. Further explanations from this table, just to put a nail on the point, the cost. Here we can see the reference bandwidth. There it is, which is 10,000. This is 10 gig. The reference bandwidth here is 10 gig. So for a 10 gigabyte Ethernet link with the speeds of 10 gigabytes per second, the cost will be 1. I think it's the same thing that we did. The cost will be 1. For a gigabit Ethernet link, the cost will be 10. For a fast Ethernet link with 100 megabytes per second, the cost will be 100. For an Ethernet link with 10 megabytes per second, the cost will be 1,000. And cost, the higher the cost, the least preferred the link will be, because it will have a very low bandwidth. It means it is very slow. All right, let's move. Cost done. OSPF accumulated cost. What are we talking of there? The cost of an OSPF route is the accumulated cost from one router to the destination network. Or assuming the auto cost reference is 10,000. Command has been configured on all three. The cost of the links between the router is now 10. The loopback interface has a default cost of 1. All right, let's use, so here we want to calculate the accumulated cost. Let's find the cost to a destination network. So if I have a network here, I have a PC in this network here, and it wants to communicate with a PC in this network. What will be the cost if I use this route, or if I use this route number 2, if I use this route. So this is route number 1, this is route number 2. If I use route number 1, the accumulated cost is, okay, let's just use the cost of the loopback interface, 1 plus 10 plus another 1, which is 12. And the cost for route number 2 is 1 plus 10 plus another 10. So this first 10 plus this 10 plus 1, which is 22. So which route will be chosen and which route will be in the routing table? This route will not be chosen because it is a higher cost. This route is the one you will see in the routing table, basically. That's how the values of cost works. Right. Okay, I think this explains what I've been explaining. Calculating the accumulated cost. We will not repeat that one. Right. OSPF accumulated cost, verify the accumulated cost path for, right. Accumulated cost. If you show the IP route, you can see this value there. The cost will be there. All right. If you go back to when we described the values in our routing table. We said the O, it represents the method, the route, the source of the route. It can be O, which means OSPF. It can be C, directly connected. We have local. We can have E, I think, which is external IGRP. We have static S. Those are the sources. We talked of this value here being the network being advertised. We have 110. What is that? 110. We also have the cost metric, which is 11. 110 administrative distance via, this is the exit interface or the next hop IP address. Needs to be remembered. Right. So from these two values, here we have the administrative distance and the cost metric. In the cost metric, it shows you the accumulated cost. What is the cost? So in this example we are doing here, we can see the accumulated cost there being calculated is 11. And from the show IP route, you can see the value. That's where the value 11 is popping up from. That's where the value, the metric 11 is popping up from. So this is all coming from the show commands. So when next time you do the show IP route, take note of those metric costs. Look at how we got to that metric cost. How did we get to that number there? Go back and try to figure out how you got to that number. Look at the interfaces that you used, calculate the cost, try to find out what is the bandwidth. Was it changed? Is it still the default? Was it changed? If not, then what is the cost? Is the accumulated cost value you calculate the same with this value right here? Use the show IP route next time and try to figure that out. That is learning. Right. Manually set the OSPF cost value. Reasons for manually setting that value. The administrator may want to influence the path selection. We know that. Number two, connections to equipment from other vendors who use different formulas to calculate OSPF cost. Right. So we have those two reasons where we want to manually configure the cost. Right. Number one, obviously to manipulate path selection, because if you manipulate the cost, you manipulate path selection. Number two, everything we are doing here, the way we are calculating our cost is for Cisco vendor. It's for the Cisco vendor. We are doing CCNA is for Cisco. But other vendors, they might calculate their values differently. Therefore, the administrator might need to manipulate those costs differently to accommodate OSPF costs calculated by other vendors. Basically, those are two reasons why we need to change the value of the set OSPF cost manually. And how do we change it? We go to the interface where we want to change and we input the value that we want to change. Test failover to backup route. What happens if the link R1, R2 goes down? Okay, I think this one can be demonstrated when we're actually doing the practical itself. But when one link goes down, what happens? The network tries to reconfigure itself. Convergence again, we go back to convergence, it reconfigures itself, it recalculates all the links, all the costs are recalculated, and we'll find another route which has a lower cost to use. Basically, that is what happens. Right? Yellow packet intervals. Right. OSPF hello packets are transmitted to multicast addresses 224.0.0.5 every 10 seconds. This is the default timer value. Yellow packets are not sent on interfaces set to passive. We did that. The dead interval is the period that the router waits to receive a hello packet before declaring a neighbor down. If the dead interval expires, the router receives a hello before the router receives a hello packet, OSPF removes that neighbor from the LSDB. Cisco uses default 4 times the hello interval. This is 40 seconds on multi-access and point-to-point networks. All right, summary. Talking of the hello interval, I think we've discussed in module 1, even in 2, what is the hello packet? The hello packet is basically used the beginning of forming adjacency. That is the beginning of forming adjacency. Hello, how are you? Hello, I'm okay. My name is router ID 111. My name is router ID 2222. That exchange, it starts with the hello packet. So how often is a hello packet sent to other neighboring routers? How often? By default, 10 seconds. So every 10 seconds, a hello packet is being sent. And when another neighbor receives that hello packet and it sends its own hello packet, we are close to adjacency. Every 10 seconds, it is being sent, right? We have the dead interval, which is 4 times 40 seconds, right? After we formed adjacency, the hello packets continue to be sent. After we formed adjacency, we are now even sending our DBDs. Hello packets, they don't stop being sent. Every 10 seconds, they are being sent. Now, if a router does not receive a hello packet after 40 seconds, it automatically means my neighbor is no longer there. If I don't receive hello packets from my next door, it means my next door is no longer there. What does that mean? It means I will need to reconfigure my networks because my neighbor is no longer there. If my neighbor it gave me some DBDs describing other networks which are neighborly to my neighbor, now that my neighbor is down, I'm not able to reach those networks because I was reaching those networks through my neighbor. So after 40 seconds, if I don't receive the hello packets, it means my neighbor is down. The network reconfigures again. I think that is the significance of the hello intervals, hello packet intervals, and the dead intervals. Right, these values, they need to be, okay, the hello interval, it needs to be very small. So that ndizive nekukurumidza kuti is my neighbor still there or not. Because ndikasaziva nekukurumidza, what happens is traffic inosendwa kuma-networks asiri kuexista are down already without you knowing. So it's very important to understand the significance of the hello packet intervals and the dead intervals. All right. Questions which typically come. I think I've seen a lot this question. If the hello interval is 10 seconds, what will be the dead? 10 times 4. If it is 15 seconds, what will be the dead? 60 seconds. 4 times the hello interval. Cheap questions, I think. All right, verifying the hello and dead intervals. Show commands. Show IP OSPF interface. You can see from that command, we can see the dead and hello intervals there. A lot of information. We can see we've talked of the network point to point. We've talked of that one. We've talked of the cost of is there as well from that show command. So it's high time you now understand, make an effort to understand if I have a show command, what is it showing me? It's very important. The show commands are very important at this stage. What are the show commands showing me? So for this one, it shows you the hello and dead intervals. Right? It also has the router ID. I can see the router ID, the process ID as well. Quite a number of things there. Use the show IP OSPF neighbor command to see the dead time counting down from 40 seconds. Okay, so if I show this OSPF neighbor, you can see the dead time counting down. So before it counts down to 0, and if it receives a packet, it goes back to 40 and it starts counting down again because it receives a packet. But if it counts down to 0 without receiving a packet, then it means my neighbor is down. The network starts reconfiguring itself again. Modifying OSPF intervals. Right. If the intervals are made less, it means the routes detect the network failures in less time. I've talked about that. And this increases traffic. This increases the traffic, but it helps with faster convergence. So the default being 10, this is the value that we have, the default being 10. Others may choose to have the hello interval at 15. The problem with having hello interval at 15, let's start with the advantage. The advantage is you don't have more frequency of those messages being sent. So they are being sent only after 15 seconds, right? Which is okay because the router does not need to process more frequently the hello packets. But the problem comes now when the dead interval is 60 seconds. So the router has to wait for 60 seconds before realizing the neighbor is down. That's where the problem is. More time before realizing the neighbor is down. The neighboring networks are down. So if you don't realize the neighbor is down, you continue forwarding packets there, but they continue being dropped. Network down. Users are complaining, network is down, network is down. But the router is forwarding to a network that has a neighbor which is down. So that's the problem. So the values need to be less. So they can be changed. Changing them to less, I've not seen less than 10 so far, but changing them, let's say you change them to less than 10. What it means, the routers will detect a router down in less time, which is very good for convergence. Basically, that's it. That's the reason why we need to change these values. You can change them. Use the no ISPF hello interval, no ISPF dead interval commands to reset the intervals to their default. So if you want to reset them to their default, which is 10, you use the no command, basically. Right, modifying them. Here we can see they were modified to 5, and the dead interval became 20 instead of 40. 5 seconds, every 5 seconds, a hello packet is being sent, every 5 seconds, which means every 20 seconds, if you don't hear anything, then that's when we will make the change. It's much better to have 20 seconds instead of 60 seconds. 60 seconds, it's a whole minute. So a whole minute, a network might not even function and you don't know it. That's the significance of those intervals there. Right. Default route propagation. Right. What do we have here? To propagate a default route, the edge router must be configured with the following. Right. What is a default route? In our, where is our network? Let me see. Voila, here. Eh, Running out of time again. All right, a default route. In this network, if we have a packet which does not have an IP addresses that matches this network that we have here, we configure a default route. In this example, a default route needs to be configured on router 2 so that every packet which is not matched, we configure it to go to the internet. Right? Now, once that default route is configured here, with IP static, we manually configure that route. With OSPF, we tell every router that this is your default route. How do we tell it? Go back to number 50. How do we tell it? We tell every router with this command. Where is it? Right. Default information originate router configuration mode. So this instructs router 2 to be the source of default route information and propagate the default static route in OSPF updates. So in all the updates that we have, we tell every router that if you have a packet which is not matched, therefore is destined to the default route, this is the address you are going to use. So instead of manually configuring at every router what is the default route, we configure on the router which is directly connected to the default route. Then we tell that router to tell every other router in the network, this is your default route, this is what you need to use. Basically, that is what the default originate command does. Here we can see the show commands in action, show IP route. So we can see, in this case, the first one, this was statically configured. And in this one, we have, this one was OSPF land. OSPF land. So this route was land via OSPF. This one was land on R2. We manually configure the route, the default route. After we manually configure the route, this is our R2, by the way. This is our R2, which goes to the internet. And this is the manual configuration. This is the interface we manually configure. And this is the one that we have here. But how does this router in the network know? How does this router know the default route? That's where the default route configuration command comes in. And this router propagates in updates to our default route and the RIP. Now, if you go to this and if you show the IP route, it will display this default route because it is OSPF land. It is OSPF land from the default originate. What is this? Default information originate command. Okay, right. Verifying single area OSPF. I think we are done. These are the commands which we are going to use to verify. I want us to take note of this. Show IP OSPF. Right. This show command can either show the database. The database, it shows you the topology table. The topology table shows you every router in the network and what is its ID. So if you go and you say show IP OSPF database, it shows you every topology in the table, right? If you go and say show IP OSPF neighbor, it shows you the neighbor table. It shows you the neighbors of your router and the information, the statuses of the neighbors of your router. If you go to show IP, okay, these two, last one, let's have one last one. If you go to show IP route, this one shows you the routing table. So I want to focus on these three show commands. The show IP OSPF database, show IP OSPF neighbor, and the show IP route. It shows you the three tables which are very important in routing: the topology table, the neighbor table, and the routing table. Every other show command, we'll learn about those as we do our practice, etc., etc. Right, so this is our show neighbor, and it is showing us the neighbors. So I'm sure this is router number 1, ID 11111. And what are the neighbors? 333 and 222. We have the show IP protocols. It gives us the router ID is there. I can see the router ID. I can also see, what else do I see? Okay, I can also see the neighbors there and the distances as well. Right, that is show IP protocols. This includes the process ID, the router ID. Okay, this is the information being forwarded, the process ID, router ID. Interface is explicitly configured to advertise the route. The neighbors, I can see the administrative distance. So some of these show commands, they show almost the same information. So it just depends on what information you are looking for in specific command that you will have to use. So this one is show IP OSPF, and that is what it shows. You can see it has the router ID, the process ID as well. What else? The show IP OSPF interface. This one shows us, most importantly, I think, it shows us if the network is a point-to-point or a broadcast. That's very important. If it's a point-to-point, no DR election. If it's a broadcast, we have a DR election. We also have the process, router ID, and the cost values from the interface command. What else do we have? Okay, the show IP OSPF interface brief. Interface is participating, the networks being advertised, the costs, the network states. So the show commands, I think, in summary, it just depends on what information you want. And you need to know, if I'm looking for this specific information, which show command am I supposed to use? And basically that summarizes, that closes our module. That's not a summary. Thank you very much for giving me your attention. That ends our configurations. The next lesson we'll actually do a packet tracer practice instead of talking configurations. I thank you again.